So this was the first HERS certified net zero energy home in California. We are proud to say it was kind of by accident. Here's our HERS certificate here, a -1. Wow. We got a -1, and the Energy Commission found out, and they sent all kinds of auditors and all this kind of stuff, and they said, yep, you're the first, and there it is, and they drafted a special resolution of recognition specifically for our company, so we were pretty excited about that. Okay, this is a hairdryer house. Here's our local Willow Glen city council member who was at a dedication. We have a video on YouTube, just Google the hairdryer home, and you can see it. And the story behind the hairdryer is I read a New York Times article in 2007 or something, many, many years ago, that indicated this, talked about passive house and that you could actually heat these buildings with a hairdryer. And I said, what? That can't be true. Interesting. Found one, built one, and I said, I got to try it. So we did, and you can look at the video, and yeah, it really works. There's so much.
There's no furnace or heater.
Well, I'll go over the mechanicals. But the idea is that you could use a hairdryer. Not a very efficient way to go. Poor coefficient of performance, but you could use it. So, in a pinch, it's a resilient building, right? Okay.
Solar-powered hairdryer?
Be good. Lots of panels. There is panels on this. Okay, so in this building, this is the net zero energy model. So it was passive house plus renewables. And here's the thing, conceptually. Here's the PG&E data on an average 3,000 square foot home in our area. Would have taken, if you take the gas, convert it to kilowatt hours, about 40,000 kilowatt hours, roughly distributed sort of this way. But almost half of it, 40 to 50% in HVAC costs. You got lighting and plug loads, a quarter, and hot water. Okay, the idea in the design process is to conserve energy. So in this building, we did a lot of modeling and so forth. And what happened is that we were able to save, through design, 60% of the standard energy. Okay, and you'll see that most of it, okay, is the difference between this big blue pie slice over here and this little blue pie slice over here, from 20,000 kilowatt hours to 2,000 kilowatt hours, an order of magnitude of reduction. And that's where most of this comes from. And the rest of it, efficiencies in appliances and what have you. Hot water is a really tricky one. What happened here is that we just split it. We have a solar hot water system. So realistically, we could 60% of the conserved energy. And that's the idea. Save as much as you can, and then renewables take over the rest. Okay, lots of exhaustive analysis of what the loads and the budgeting. It's very tedious and so forth too, but that was done. Our production model for the energy load. So this is sort of symbolizing our array of photovoltaics on the roof, and you can see sort of a distribution, fully a third of that in appliances, and I even break out electronics because they are really beginning to suck a lot more, the DVRs and so forth. So between the two of them, those are called the miscellaneous loads, over 50% of the loads. Once you've taken all the space conditioning, which now is down to like 20% of the line loads, a little bit of lighting and cooking. And this one, we had space, and we had a kind of an interesting model. We were working in the Department of Energy, and there's source energy, not time to get into it. But we basically overproduced, okay, to offset a little bit of gas for supplementary water heating and cooking. It has a nice Viking gas range in it. Very interesting, works great with electric vehicle charging. This is not just a net zero energy home. This is a radically plus energy home that offsets about, 15 to 20,000 miles of electric vehicle driving. It's pretty amazing. Okay, so the specs on the building.
What temperature in the house in the wintertime are you targeting?
I'll show you.
Right.
Okay.
Also, did you
Basically 72 degrees, room temperature.
Did you account for landscaping? I saw there's like grass and stuff around the sprinkler.
Do we?
It's energy usage, right?
There's a whole bunch of additional.
Yeah, it's a LEED. This is a LEED platinum home, and there's all kinds of sustainable stuff. There's a gray water system and so forth. But I really, I don't want to go there. We'll get off track. So here are the specs of this building. Okay, conditioned crawl space with an ICF stem wall foundation, much like this construction ICF. Walls are 2x6 framing with dense packed cellulose and an exterior, skin of 1 inch of rigid EPS insulation. Ceiling R50, about 14 inches of loose fill, and triple pane windows, with very important shading, has a heat recovery ventilator, runs at about 115 CFM, wonderful fresh filtered air 24/7. Heating and cooling, it has a heat pump. The smallest we could buy, full split system heat pump. Only the first stage is connected. So it's 16,000, rated at only 16,000 BTUs. Really small. It's electric, air source heat pump. Okay.
What's a heat recovery ventilator?
It's a fresh air system where it's constant balanced ventilation, fresh air in from outside, exhaust air from inside, but they exchange heat through a passive heat exchanger. 70 degrees inside, 40 degrees outside. So 40 degree air coming in exchanges heat with a 70 degree air going out, and you only lose about 15% maximum of that heat. So the incoming air would be tempered to about 64 degrees. So you don't even, very comfortable and so forth. And very efficient, you'll see that. Okay, and you can see we passed all the passive house specs with air tightness and what have you. So quickly, shading, as this gentleman, you're a good straight man over there, someone who said about sun and shading. And yes, this is in San Jose, and you'll see we'll go through some of what the modeling tool helped us to figure out. But shading, very critical. So in these southern exposures, we have 3-foot wide overhangs on the trusses. That one's 4. All of these areas here, as you can see, have specifically designed shades to be able to, you can see at this point here, there's no direct solar gain on these windows. On the west, sun's always low. These are actually solar-powered vertical shade screens that block out about 90% of the solar gain, but keep some of the light. Okay, so we'll start talking about performance now. So this was a thermograph, kind of interesting. Again, we rainbows and all sorts of stuff. We love to look at this stuff.
Good question over there.
Are you talking about cost at all?
Mm-hmm. I knew that question would come up. You bet. Okay, so here's the thermograph taken. Unfortunately, it's not quite late enough at night so it has a little residual heat. For example, in the front, there hasn't been enough time. This is stone here, Western Sun. So this had a lot of absorbed heat and needs another 4 or 5 hours to lose it. But you can see the difference here. This is the top of the house, okay, triple pane windows, et cetera, and the specs that I told you. Here's the German window here, and you can see that this profile here of a double-stepped seal, 2 rubber seals, firmly, there's absolutely no heat leaking anywhere. And the interesting thing is that these windows actually are so efficient, they get frost on the outside. Think about that one. They frost up on the outside. Okay, keep going.
What time of day is this?
This is at midnight. This is like midnight, okay? Here downstairs, this is the
It takes about January.
yeah, this is not part of the thermal envelope. It's just the garage, not air sealed or anything like that. And here's the front porch. There's a lot of residual heat. But the thing I wanted to point out, this is the American door, with the red spots. That's where the heat's leaking out. We tried as hard as we could to get manufacturers, but that's as good as we could get, okay? Okay, so what are the numbers like? So first thing is the summary, okay? First, year 1 of data. Total HVAC costs 68 cents a day. Okay, if you had to buy the energy. In this case, they don't have to buy anything. But so you can make a comparison. If you were buying, if you didn't have the solar panels, that's what it costs.
What's a typical house compared?
Well, if you go back to the typical 3,000 square foot house,
Yeah.
right? You had 40,000 kilowatt hours. It's typical because a lot of it has to do with gas and so forth. And it's just the space conditioning cost. But it would be closer to, I don't have that number. It's a good question because this includes the cooling season as well.
Double that or something?
Oh, way more than that. Yeah, way more. Many times that. Thermal comfort, average was 73 degrees, plus or minus 2 degrees. It's a set it and forget it, okay? You just leave it on, and it modulates itself, okay? And amazing indoor air quality and comfort because it's fresh, filtered, positive ventilation, and remarkably even temperatures. Here again, the data, the PHPP had said about 1280. We actually used 1150. Total was pretty close. Average Okay, so what happens in this building, this is high ceilings, it's about 21 or 22 feet vertically here. Okay, the average across between first and second, the average temperature differential was less than half a degree Fahrenheit. Okay, there's no stratification in this building. We'll talk about that's one of the characteristics. Heat pump performed amazingly. I'll give you some more data here. We'll keep going.
So those number, are those pre-solar number or with all solar?
No, the
HPV and actual.
well, this is the model. This is the passive house model. So this is when we designed the building, and we went through all those variables, and we said, okay, we're going to meet it. The model,
Is solar calculated into that equation?
no, no. The solar was completely separate. So the message here, it was extremely accurate. It was like within, within 10%. Okay, what happens here? I'm going to go kind of quickly on these things. Here's the profile of energy use. Almost a third of it was actually going into electric vehicle charging. So that's electric vehicle charging here. These are the plug loads here, appliances, lighting, etc. Let's see, this year, I don't know what it is. He changed it. It's a RAV something. I can't remember. Total. Yeah, we had the first time we had a Nissan. Okay.
Tesla?
No, it wasn't a Tesla. This one's hard to read, but just quickly. So what happens here is just the loads are stacked on each other. Here's the temperature graph, and it's just kind of showing what happens. So at the base load is the HVAC. This particular period here, because we had a hot spell, it was up in the 90s and so forth too. So it increased. Here they were on vacation. This blue stuff, this is when you got the electric vehicle, and this is the electric vehicle. You can't read it much, so I'm not going to spend much time on it. This here is what tells us.
Sorry, I was just curious, what system do you have to be able to get the basically the breakdown of energy consumption in the house? Is there something that monitors?
You'd have to ask the partners, Davis Energy Group. They do all the modeling and so forth in this particular, case. Yes, sir.
Does your energy modeling assume that windows are closed 24/7?
No, you can actually modify that and switch to natural ventilation in the summer. But you can actually model both scenarios. So
The model that you with these numbers is just assume the windows are closed all the time, and people are not opening their windows.
Actually, the way that I modeled this for cooling, and we're going to go there right now, so is that we modeled it that way. Because our experience has been that occupants are not terribly reliable. But Brahma is correct. You can model it any way you want.
I just want to know how you modeled it here. To yield those numbers, if you assume the windows are closed all the time.
That is correct. Yeah.
Okay.
Okay.
Windows all the time.
This is production against the spikes in loads. So net production here. The important number here is that we're at 105% of house energy for this. I don't know which period this is in year 2 so far. That's like 8 months or something, and that includes the electric vehicle at this point. So we know we're very, very much net zero, beyond net zero. This is just monthly, and it includes a little gas. That's why I threw it up here. Less than a therm a month when hot water is working, and just a few during the winter. Very minimal gas usage. Average PV production is here, so you can see the loads of these are the plug loads, all the appliances and everything. This is the HVAC, and then this here is the electric vehicle. And you can see how that
Quick
works.
question, so wait, isn't the electrical vehicle charging at night?
Yes.
So how are you storing, you have a battery storage?
No, it's grid-tied. It's a grid-tied system. And one of the great things about this, since you asked the question, is there's some great economics here, right? Because the peak energy is being, the meter's spinning backward and being sold, the energy is sold to PG&E during summer afternoons, right? We're getting 28 cents a kilowatt hour, right? Guess what? You're charging your vehicle, time of use tariff, okay, and you're buying it back at 10 cents. It's really great. So that's what's the 15 to 20,000 miles. It's wonderful. Yes, sir.
PG&E is heavily lobbying PUC to change.
I understand, but right now these people are understanding it. Yeah, gee, I wonder why. But actually, because remember what you're doing is.
15 more minutes.
Okay, remember what you're doing is you're offsetting peak loads. Okay, so there's a very useful function that's going on there. You're flattening the demand curve. Okay. So quickly, we'll talk about the mechanical systems now, because what happens in these buildings, they behave differently, right? Because you've dramatically, by an order of magnitude, reduced your loads. Okay, so it acts differently as well. So you have to understand this when you're designing. So the physics are the same, but the behaviors are different because our loads are low. And it's very highly, thermally sensitive. And you have this ventilation, so you have moving air, okay? So the stack effect, right, which usually is driven by temperature differentials, okay, it just doesn't apply, right, because there's no temperature stratification. So if this is done, we're moving air all the time, and the loads are so low, and we don't have any infiltration or exfiltration that's not controlled, so we just don't have any meaningful stack effect. We don't have these big temperature setbacks where the building absorbs a lot of energy and then warms up and then it cools down. It just stays very evenly temperatured. And when you build these now, they're spending a little extra money in the case of residential scale. When we get to larger scales, it can go the other way, where you actually save money because you're reducing the need for mechanical systems, much simpler and less money. So there's sort of a curve function in there. And you really need the caution, you really need to understand, you really need to model and understand how these buildings behave, or otherwise you get in trouble. So the first part when we modeled this building, let's try to go through this quickly, okay, was this warning from the model. Warning, 18.7% of the time you're going to overheat. That's 68 days or pretty much every day of the summer. Okay, so we took that seriously and we looked at the energy balance equations. Okay, internal gains, obviously in solar, but just the internals, you don't have to read this, occupants, electrical usage, etc. We got at least 75,000 BTUs of internal heat, at least, plus the solar gains. So we know you have to get rid of heat every single day. So we started this model with this 18%, assuming, okay, if we don't open windows and we don't count on breezes and we don't have any kind of extra thing, what's going to happen? That's where we started, okay? And then we used the modeling tool, okay, which is...
So just to answer the gentleman's question, in terms we modeled the worst case scenario, closed windows, because that's where we have to design to the most conservative level and assume that occupants will not open windows. So that's just to
Yes,
clarify that.
right. But here's a case where in this building we had the ability to use night ventilation cooling because we get great temperature deltas here in this particular climate zone. Okay, so we modeled this for an automated night ventilation, okay, at 2 air changes per hour, 800 CFM, not really that much for that size building. That's 3,200 square feet, 34,000 cubic feet, pretty big building, okay? And it says, oh, you can remove almost 90,000 BTUs of heat every day, and you're not going to overheat. Boom. That was our forecast. What were our results? My favorite, night ventilation cooling. Here's the data from Building America. These are just the different temperature zones. The bottom line is this. Over 146 days that they measured, we removed an average of 100,000 BTUs of heat through using a fan, an integrated fan. We call it night ventilation cooling. Operating at about 700 degrees. Cost was about 2 kilowatt hours. If you were paying for it, it'd be about 20 cents a day. Next to nothing in terms of efficiency. Here are the systems in the house. That night breeze operated at an EER of 53. Now, not everyone knows what that is, but it's a measure. You know when you buy an air conditioner, you get a SEER rating, SEER 13. Okay, well, you knock down a little bit to get the actual number, like 80 or 90%. So the average for SEER 13 would be about maybe 10 or 11 actual EER. This is 5 times as efficient because you're just running a highly efficient fan. The heat pump we used was really good, SEER almost 21, and the HRV, when they did the math on that one, is at about 20. Very, very efficient equipment. Now, you see what happens here. Here we get into the comfort in the interior. These are interior temperatures. This is the exterior. This is the diurnal cycle. This is over a hot day in May. This is up into the 90s, or a hot week. And you see what happens in night ventilation cooling is that it warms a few degrees over the day. Night ventilation cools the mass, etc. And we have about just a 5 degree temperature swing. It was typically between about 70 and 75. Okay. Wonderful. Just wonderful.
Does VSP beam modeling allow you to do ground source heat pump
Oh, yeah.
as well? Oh, okay, good.
Okay. Now, we had to turn the night ventilation off because they wanted to gather, the data team wanted, he said, hey, we're not getting any data on the heat pump because it never goes on for cooling. You don't need it. So we turned it off right there, okay? And we looked again at these temperatures, and they changed. Instead of this little cycle here, and you can see all the temperatures are really close, But what happens is that now we don't have that nighttime, that full cycle, and things sort of start to even out.